Assalamualaikum warahmatullahi wabarakatuh. A very good day. So for chapter number 5, part number 3, we will discuss about stage reaction for axial flow compressor. Degree of reaction or reaction ratio. So the figure shows the arrangement of rotor blade rows and also stator blade rows, including the velocity diagram at the inlet and also at the outlet of the rotor blade rows. Okay, for degree of reaction formula, if we consider for the ideal flow condition where we assume that the flow is incompressible and also reversible, the general reaction equation for the degree of reaction actually based on the static pressure difference, where the equation represented by equation number 1, where R, degree of reaction, equal to P2 minus P1 divided by P3 minus P1, where P2 minus P1 represent the static pressure difference in rotor, and P3 minus P1 represent the static pressure difference in a stage of the compressor. For the actual flow condition, where we consider the flow is compressible and also irreversible, the general reaction equation is based on the static enthalpy difference, where R formula, degree of reaction formula, is equal to H2 minus H1 divided by H3 minus H1, represented by equation number 2, where H2 minus H1 is equal to the static enthalpy difference in the rotor, and H3 minus H1 is the static enthalpy difference in the stage of the compressor. Across the rotor, we know that the relative stagnation enthalpy is constant, so we will have H02 relative equal to H01 relative, represented by equation number 3. And the basic equation for the relative stagnation enthalpy is shown by equation number 4, where H stagnation relative enthalpy equal to static enthalpy plus half W square. Manipulate equation number 4 and substitute into equation number 3, so we'll get the formula for static enthalpy difference in the rotor, where H2 minus H1 equal to half W1 square minus W2 square, represented by equation number 5. If we consider normal stage condition in order to simplify the analysis, the normal stage condition refer to the inlet and also the outlet condition of a stage at constant condition, where C1 equal to C3 and alpha 1 equal to alpha 3. So manipulate the basic stagnation enthalpy equation in equation number 6 and substitute into the static enthalpy difference term for a stage in equation number 2. So now the equation number 2 will change to equation number 7, where H3 minus H1 equal to H03 minus H01. And further, if we consider Euler equation, H03 minus H01 also equal to U multiplied by CY2 minus CY1, represented by equation number 7. Substitute equation number 5 and also equation number 7 into equation number 2. So we'll get new expression for degree of reaction, where R equal to W1 square minus W2 square divided by 2U multiplied by CY2 minus CY1. Equation number 8. Okay, further, if we add one more condition, which is referred to the constant axial velocity condition, where Cx1 equal to Cx2 equal to Cx3, where the axial velocity condition throughout the compression ratio is constant, and we consider the triangle law and also velocity diagram shown in the figure, we know that W square will be equal to Cx square plus Wy square. So implement the relationship. So the term of W1 square minus W2 square in equation 8 will be equal to Wy1 square minus Wy2 square, as shown in equation number 9. Substitute equation number 9 into equation number 8. So we'll get another new expression for degree of reaction where R equal to Wy1 square minus Wy2 square divided by 2U multiplied by Cy2 minus Cy1, represented by equation number 10. So based on the velocity diagrams in the figure, so we know that Cy1 equal to U minus Wy1, equation number 11. Cy2 equal to U minus Wy2, equation number 12. So implement quadratic equation principle to equation number 10 and substitute equation 11 and 12 into equation number 10. So we'll get more simplified degree of reaction equation where R equal to Wy1 plus Wy2 divided by 2U, represented by equation 13. So if you want to include the relative flow angle, so we can base on the relative mean angle beta m equation, where tangent beta m equal to half multiplied by tangent beta 1 plus tangent beta 2, equation 14. Okay, substitute into equation of degree of reaction, so we'll get R equal to Cx divided by U multiplied by tangent beta m, represented by equation 15. For the degree of reaction equation that based on beta 2 and also alpha 1, so we'll have equation number 16 where R equal to half plus Cx over U2 multiplied by tangent beta 2 minus tangent alpha 1. Choice of reaction. So now we will discuss or call how to choose the proper value of degree of reaction for the axial flow compressor. So degree of reaction R is a design parameter which has an important influence on stage efficiency. So we need to choose correct reaction degree of reaction value in order to obtain optimum stage efficiency for the compressor. So in order to discuss the choice of reaction, we will base on the equation number 1. The equation for degree of reaction where R equal to half plus Cx divided by 2U multiplied by tangent beta 2 minus tangent alpha 1. Okay, so there are 3 categories of reaction in this slide. So first we have 50% reaction stage where the value of R equal to 0.5. So in terms of characteristic, if you look at the velocity diagram at the inlet and also at the outlet of the rotor, so we will have symmetrical velocity diagram as shown in the figure, where the main criteria for this reaction stage, where the value of alpha 1 equal to the value of beta 2. So R equal to 0.5 is widely used due to the adverse pressure gradient are equally shared in the rotor and also stator rolls. So if you look in the schematic diagram, the schematic diagram shows the pressure profile throughout the compressor stage, where we can see clearly in terms of static pressure difference in the stator is equal to static pressure difference in the rotor. And static enthalpy difference in the stator also equal to static enthalpy difference in the rotor. So for this degree of reaction equal to 0.5, the pressure and also the enthalpy difference is equally shared in the rotor and also stator rolls. So the condition for the R equal to 0.5 will minimize the tendency of the separation flow and also will avoid large stagnation pressure loss. So probably this value of R equal to 0.5 will give us the optimum efficiency of the axial flow compressor. The second category is for R less than 0.5. So if you look at the velocity diagram features, so the velocity diagram at the inlet and also at the outlet of the rotor, in terms of features, the velocity diagram will skew to the left as shown in the figure. And beta 2 value will be less than alpha 1 value. So for R less than 0.5, the static enthalpy rise and also static pressure rise in the stator exceed that in the rotor. So if you look to the pressure profile, we can see that the static pressure difference in the stator is greater than static pressure difference in the rotor. And also in terms of enthalpy difference, static enthalpy difference in the stator also higher than static enthalpy difference in the rotor. So the limitation for this category is we need to make sure that if we choose the degree of reaction lower than 0.5, so we need to make sure that the condition will not uh, achieve or arrive at Mach number equal to unity or equal to 1. So if this happen in the actual condition, actual operation of the axial flow compressor, the choking phenomena will occur, and this will reduce drastically the efficiency of the compressor. Okay, so the third categories is for R higher than 0.5. So in terms of velocity diagram, the features of the velocity diagram will be skewed to the right, and beta 2 value will be higher than alpha 1 value. So for R higher than 0.5, the static enthalpy rise and also static pressure rise in the rotor will exceed that in the stator. So if you look to the pressure profile in the schematic diagram for R greater than 0.5, clearly you can see that static pressure difference in the rotor higher than static pressure difference in the stator, and also the static enthalpy difference in the rotor also higher than the static enthalpy difference in the stator. So we can choose R greater than 0.5, but the limitation similar as the second category, where we need to make sure that Mach number is not equal to unity or equal to 1, because the condition will cause choking phenomena and reduce drastically the efficiency of the axial flow compressor. Example 5.2. Figure 1 shows velocity diagram for an ideal compressor stage which has no stagnation pressure losses. The stage of the compressor is considered as a normal stage where C3 equal to C1 and alpha 3 equal to alpha 1. Based on the figure 1, air enters the compressor rotor at entry angle of 10 degree with absolute velocity of 50 meter per second. The rotor blade speed is 100 meter per second. The air deflects from the rotor with absolute velocity of 80 meter per second. For normal stage compressor, the axial velocity across the stage is constant. Determine the degree of reaction for the compressor. The solution for example 5.2. So based on the data and also information given, you have to draw the velocity diagram. So alpha 1 equal to 10 degree, C1 equal to 50 meter per second, C2 equal to 80 meter per second, and U equal to 100 meter per second. Based on constant axial velocity condition, so Cx will be equal to Cx2, Cx1 equal to Cx2 equal to Cx. And the value of for Cx still not known, so we need to determine during the determination of velocity vector for the velocity diagram. And for normal stage condition, C1 equal to C3, alpha 1 equal to alpha 3. So first we try to draw the velocity diagram at the rotor inlet for condition or state number 1. And you need to make your own scale to draw the velocity diagram. Okay, so because we already know that the magnitude for u is equal to 100 meters per second, and also the direction of the u vector is in horizontal direction. So we can draw the vector for u. Okay, so by using geometric approach, we need to use a ruler, compass, and also protractor for magnitude and also angle determination, respectively. Okay, so because we already know the value of alpha 1 and also c1, so easily we can draw the line for vector c1. Okay, so from vector c1 we can determine the axial velocity value. Okay, as shown in the figure, we just draw the upper limit line and also lower limit line for the axial velocity by referring to the c1 vector. Okay, so from these two lines we can determine cx1 value measured by using the ruler. So we will get cx1 equal to 49 meter per second. So the axial velocity equal to 49 meter per second. Okay, if we also can determine the axial velocity by using trigonometric approach, where for the axial velocity, if we look to the triangle for the velocity diagram, cx1 is equal to c1 cos alpha 1, where c1 equal to 50, alpha 1 equal to 10 degrees. So we can calculate cx1 by using trigonometric approach, where the value will be equal to 49.2 meter per second. So the value that we obtain by using geometry approach and also trigonometric approach will be almost similar. Okay, next for the relative vector, so we just complete the what I call the triangle velocity triangle at the inlet of the rotor. So we just connect the initial point, so initial point for the c1 and also initial point for the u vector, so we will get the vector for w1 and measure the line. So we will get w1 equal to 103.3 meter per second. So relative flow velocity that we obtain is equal to w1 equal to 103.3 meter per second. And by using the protractor, we can measure the relative flow angle beta 1, which is equal to 61.5 degree. Okay, so the value of relative flow angle also can be determined by using trigonometry approach. So if we look at the visual diagram, we have the component for wy1 and also the component for cy1. So if we base on the trigonometry approach, tangent beta 1 is equal to wy1 divided by cx1, or equal to u minus cy1 divided by cx1. So rearrange the equation, manipulate the what I call the trigonometry. Tangent beta 1 also equal to u minus c1 sine alpha 1 divided by cx1. So we get the value for tangent beta 1 equal to 1.8560. So determine the value of beta 1. So the beta 1 value will be equal to 61.7 degree. Okay, the value is similar to the value of beta 1 that we obtained by using geometry approach. Okay, for relative flow velocity, similarly with relative flow velocity, also can be determined by using trigonometry approach, where w1 equal to cx1 divided by cos beta 1. So if we substitute the value of cx1 and also beta 1 they obtain from the trigonometry approach, substitute into the equation for w1. So we'll get the value for W1 equal to 103.8 meter per second. Okay, so the value also is quite similar with the value of W1 that we obtained from geometry approach. For rotor outlet condition, data and also information given in the question are C2 equal to 80 meter per second and U equal to 100 meter per second. And constant axial velocity condition, we know that Cx1 equal to Cx2 equal to Cx, where the value is equal to 49 meter per second. This value we already obtained from previous slide by using graphical approach or geometrical approach. And now we need to draw the velocity diagram at the rotor outlet, where still you need to use your own scale in order to obtain or in order to draw the velocity diagram at the outlet of the rotor. So first we draw the what I call the vector for u, because we already know the magnitude and also the direction of u vector. And also we know the value of axial velocity. So by using the value, we just draw the lower limit and also upper limit line for the axial velocity, where the distance is equal to 49. The distance is the distance must be represent the value of Cx equal to 49 meter per second based on your own scale. Okay, by using geometry approach or graphical approach, so you need to use a ruler, a compass, and also the protractor in order to obtain magnitude and also angle for the velocity diagram. So for absolute flow angle alpha 2, so the value is not given, so we need to use compass based on C2 information and also Cx and also the endpoint of vector u. So from the endpoint of vector u, so we need to draw a circle by using a compass. And first you need to set the compass in terms of distance that represent the value of C2 value, which is equal to 80 meter per second. Okay, then after you set the compass at the correct distance, so you need to draw what I call a circle from the endpoint of u vector. Okay, as shown in the slide. So from the line that construct by using the compass, so you can obtain the intersection point of the circle with the upper limit line of the axial flow velocity line. So from the intersection point and also from the end point of the vector u, so we can draw the vector cu line as shown in the slide, where cu equal to 80 meter per second and the value of cu already given in the question. Okay, so next, from the line we can determine by using the protractor, we can determine the value of absolute flow angle alpha 2, which is equal to 52 degree. Okay, next about relative flow velocity. So we can obtain the relative flow velocity line vector by connect the initial point for C2 and also initial point for U vector. So we can draw the line for relative flow velocity vector W2, where if you measure, we will get W2 equal to 61.3 meter per second. And also we can determine the relative flow angle by using the protractor based on the line that we already construct for W2. So beta 2 value equal to 37 degree. So all the value also can be determined by using trigonometry approach, where for absolute flow angle, if we look at the velocity diagram, we know that cos alpha 2 equal to Cx2 divided by C2. Cx2 actually equal to 49.2. So this value 49.2 actually the Cx value that we obtained from trigonometry approach from previous slide. and the value for C2 already given 80 meter per second. So we will get cos alpha 2 equal to 0.615. Determine the value of alpha 2. Alpha 2 will be equal to 52.04 degree. For relative flow velocity, if you refer to the velocity diagram, so we have the vector for Cx2, the y component of Wy2 and y component of Cy2. So by using the triangle law, we know that W2 square equal to Wy2 square plus Cx2 square. And rearrange the equation, so we'll get W2 equal to square root Wy2 square plus Cx2 square. Calculate the value of W2, so we'll get W2 equal to 61.5 meter per second. For relative flow angle, beta 2, refer to the velocity diagram. So cos beta 2 equal to Wx2 divided by W2. W2 equal to 61.5. However, Wx2 we obtain from the value of Cx2 because for this problem we consider that the axial velocity is constant throughout the compressor stage, where the value of Cx1 equal to Cx2 equal to Cx3. Similarly with the relative component, where Wx1 also equal to Wx2 equal to Wx3 equal to Cx value, which is equal to 49.2 if we base to the value they obtained from the trigonometry approach in previous slide. So we will get cos beta 2 equal to 0.8. Calculate beta 2. So beta 2 equal to 39.3. Beta 2 is equal to 36.9 degree. So if you compare to the value that we obtain for both approaches, so the value is almost similar. So from the value that we obtain for the velocity diagram, so we can determine the degree of reaction. So we need to choose. There are many equations for degree of reaction, but we need to choose the proper degree of reaction equation based on the data that we obtain. So now for this slide, for this question, I use this degree of reaction equation where R equal to half plus Cx divided by 2u multiplied by tangent beta 2 minus tangent alpha 1. So if we substitute all the data that we obtain into the equation of degree of reaction, so the value of R will be equal to 0.73. Okay, to test your understanding for part number 3, chapter number 5, answer the question below. First question, give one reason why R equal to 0.5 is widely used in compressor design. Question number 2, give two approaches that can be used to solve problem involving velocity diagram. Question number 3, base parameter of reaction for ideal flow condition. What is the base parameter of reaction for ideal flow condition? So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue is also given in the link. So that's all for part number 3, chapter number 5. Assalamualaikum.